to have you today, and I'm here with Jonah Shine, who has worked on the WaterSense program for many years now, on the WaterSense labeled homes program, as well as many other aspects of the program over time. So I'm excited to hear what he has to say today. I'll just put things over to you, Jonah.
Thanks, Tara, and thanks for abiding by our agreement to not say how many years. Tara and I
Yep.
struck that bargain just before we went on because I told her that it was starting to date us both.
Yep.
But thanks for having me. Thanks everyone for coming. We're going to talk about the connection of water, energy, and carbon today. I think probably most participants on the webinar today are here because you acknowledge that this connection exists. But I think a lot of the times it tends to be spoken about, in my experience, at this really high level, and that's fine. There's nothing wrong with that. But I think there's a benefit to really sort of getting into the details, talking about the ways that saving water can help save energy, and really getting into the minutia of how we can quantify it and how we can make an impact. So that's what we're going to try to really focus on today. Just as a reminder, this webinar is part of a series. We're almost at the end of the year, so we only have one of these left. But everything we've done as part of this series up until this point is available in recorded webinars on the website. And that's an important thing to call out because this webinar is going to be a little bit different than a lot of the other ones in this series. I think there's a real conscious effort from Tara and from the other people that help put these on to make these webinars very applied and really give very concrete advice on how you can improve water management in your facilities in different ways. This webinar is going to be a little bit more conceptual. And if you take only one thing away, hopefully it's that by saving water, you can save a whole lot of energy. We'll touch on some of the ways that you can do that, but we're not going to get into a lot of the details. We'll talk more about sort of what the areas you might want to focus on are, and then we'll refer you back to a lot of these other resources and other webinars that have really dug into details on things like restrooms or mechanical systems for the nitty gritty know-how of how to apply projects in your facilities. So like I said, that sort of will be the general twist of the webinar today. Give you a little bit of a background on WaterSense, and then we're going to talk about the intersection of water and energy really in three ways. Number one, we'll talk about the embedded energy, so the sort of energy that's gone into water, so to speak, in order to get it to the point of use to customers in a clean, healthy, safe way. And I'll share a case study about that to help illustrate exactly how much energy may be in water, at least in this particular case, and the different factors that influence that. That case study will also lead us straight into discussion of water heating, which is a really big place where the connection between water and energy and carbon exists. And then finally, we'll talk a little bit about processed water and cooling towers, which is one of the places where the connection gets perhaps a little bit more complicated because with the embedded energy and with water heating, it's all very straightforward. Use less water, you will use less energy. With cooling towers, it's a little bit more of a trade-off, and we have to weigh those things sort of carefully. So just a quick refresher about WaterSense for anyone who doesn't know. WaterSense is a voluntary program. It's an EPA program. We've been around since 2006, and it provides a really simple way to identify high-performant, water-efficient products, programs, practices, and homes. We also have a whole house home certification, which will be the subject of the case study that I'll talk about before. When you see the WaterSense label, one of the things that we really try to embody in that brand is that it's a certification that stands for water efficiency and performance. So not only do WaterSense labeled products save water, but they also are third-party certified to ensure that they work the way users expect products to work. So you flush a toilet, it's going to work properly the first time. You get in a shower, it's actually going to feel like a shower because we do have protocols to ensure that that's the case. So like I said, the subject of the webinar today is really going to be on this connection, the nexus between water and energy. And every gallon of water that you use has a footprint. It comes from the energy that's needed to pump, move, heat, treat it, and get it to the customer. So like I said, this all gets a little bit confusing. If you want the cliff notes, it would be that if you save water, you're going to save energy. But I also do want to underscore that when it comes to things like mechanical systems and cooling towers, we really do think that evaluating water and energy efficiency together provides the best result and is going to get the most efficient result for any given facility. The other thing I'm not going to talk a lot about, but I do want to acknowledge is that, as I said, there's a lot of energy required to support the water that we use, but the opposite is also true. There's a lot of water needed for our electric generation. In fact, if you just look at water withdrawals, so the water that we take out of our systems, our groundwater, our streams, our lakes, our reservoirs every day, thermoelectric power generation is actually the largest user of water. But again, let me emphasize that this is withdrawals. That's not the same as use, or that's not the same as a consumptive use. So one of the things I've seen a lot of people do is if you do the math on this 41%, so we withdraw about 322 billion gallons of water every day, according to the most recent complete USGS data. If you just look at that 41% that we use for thermoelectric generation and factor in the amount of electricity that we generate, that comes out to about 13 gallons per kilowatt hour. So something I've seen a lot of people do in the past is look at savings and say, oh well, I've saved say 100 kilowatt hours. That means that that 100 kilowatt hours has equated to 1,300 gallons of water savings, and that's not exactly accurate. Because just because we withdraw 13 gallons doesn't mean that we've actually consumed and made that 13 gallons unavailable for another purpose. In fact, in thermoelectric generation, we get a lot of that water back. So again, big part of our overall water management structure, but it would be incorrect to say that we actually use 41% of our water for power generation. The other thing that doesn't show up if you're just looking at withdrawals is hydroelectric power. And this is actually one of the more consumptive users of water, because when you spread water out, as you do in a reservoir, behind a hydroelectric dam, you really increase the surface area and you really increase the evaporative loss. Now, it doesn't show up in this data because we're not actually withdrawing anything from the reservoir. It's just evaporating normally, but it does impact the amount of available water quite significantly. And increasingly out west, it's becoming an important piece of the water management puzzle. So if you, it's a pretty dense document. I don't suppose a lot of people read every page of Department of Interior's impact analysis last year on the Colorado River. But one of the scenarios that they explored and concluded would just be sort of so catastrophic for the country it couldn't even really be entertained was the idea of letting the dams out west, the reservoirs, go to dead pool, where they would no longer be able to generate hydroelectric power. So like I said, doesn't show up in this in here, but a very real part of how we manage water. Just want to acknowledge that because we're going to spend most of our time in this webinar talking about the other side, the energy that goes into supporting our water systems. And that energy, once it goes in, it is gone. Right? We've generated it, all the carbon that's associated with the generation of that electricity, of that energy that we use, is now a part of our emissions, and we can't do a whole lot about it. So, as I mentioned, every gallon of water's got that energy footprint. So moving, treating, heating, all those things that use energy. But of course, the natural question is, well, how much? And the truth is, we don't really know. It's not because this data doesn't exist, it's because it's not aggregated in one place. So I've put up some estimates. One that's quoted a lot is that almost 20% of electricity in California is consumed by pumping, heating, and treating water. There's other estimates that say water-related energy uses account for more than 500 terawatt hours a year. That'd be more than 14% of total consumption for 2020 in the U.S. There's estimates that say that the water sector accounts for 4% of global electricity consumption. There's also some estimates that say the U.S. water sector accounts specifically for 2%. So really just the water suppliers as an industrial sector account for 2% of total energy use. So like I said, nobody really knows, but if I were to give you an executive summary of all of the data that's out there and all the different studies, it would simply be to say a lot. It's a lot of energy that's embedded in our water. To jump into the case study and really talk about how we get to a more granular estimate. So again, not big picture, hypotheticals, but for a specific project, in this case, a specific community, because of its specific location, the way that it's built, its local water sources, and the things we have to do to get water to that location. What is the energy profile of water at this location? And the things we have to consider there is, well, first and foremost, there's extraction. We have to get the water out, whether that's groundwater, surface water that we pump out of a lake. There's energy associated with that pump. There's conveyance. We're going to have to move it from where it is to where we want it. We'll then use energy for treatment to get it to be nice and clean and healthy and safe for everybody. We'll use distribution to get it out to homes and businesses and facilities where we want to use it. Anything that, and then for some water, that will sort of be the end of the road. We use it outside, or we use it for something like a cooling tower where the water is going to evaporate. That's the end of its profile. If it goes inside the building or inside the home and we do something like, say, heat it, that's going to increase, that's another sink of energy. And then wastewater, finally, is also what's going to take energy to collect and transport, and then once again, treat that water. So this is sort of all of the different things that are variable. They vary from location to location, from place to place, and they impact this question of how much energy is in the water, right? When you take a gallon of water out of the tap, how much energy is represented by that gallon, and how much energy and carbon can save. The bad news is that the data indicates to us that just about everything, with the exception of one element on this that I have up here right now, is actually going up. It's actually becoming more intense for a variety of reasons. Extraction, because we're having to get new water resources. Well, the easy water resources are already being used, right? There's a reason people went to the low-hanging fruit first. So additional water resources do tend to have higher extraction, higher conveyance, energy associated with them. They also tend to have higher treatment, right? So the reason a water source might be a secondary choice could be because of its location, but it could also be because of its quality. We have technologies to treat lower quality water, but they're more energy intense. And then distribution, again, when we build a new treatment facility or a new filtration plant, but it's further out, or when we build a new community and it's further out from the existing infrastructure, that all means that we're using more energy to get the water where it needs to be. On the flip side, wastewater the energy intensity of wastewater treatment is primarily going up because wastewater treatment plants are having to do things to get the water cleaner. That's in a large part to regulations from us, from the EPA, regarding what the effluent from wastewater treatment plants can contain. And hopefully we can all agree that having cleaner water is ultimately a good thing, but it is having an impact to make the energy intensity of wastewater treatment more intense.
Hey, Jonah, you're kind of trailing off at the end of your sentences, so it's kind of hard to hear you at the end.
Sorry, is that any better?
Yeah, that's better.
Okay, I'll try to keep my headset nice and close. Water heating is the one thing on this list right now that is actually becoming more efficient. And a lot of you will probably guess, there's two reasons for it. One, you'll probably guess that we're actually getting more efficient water heaters. So when we have technologies like heat pump water heaters, those make the energy embedded in hot water a lot lower. The other, looking at a national level, is actually because the population continues to move to warmer parts of the country, and we use less water. We use less energy to heat hot water when it's in a warmer climate as opposed to a cold climate. So that's the one that's going down. Everything else is becoming more intense and increasing the energy that we use in regards to water. Tara, am I sounding okay? Or do you need me to switch headsets?
No, you're just sounding quieter at the end of your sentences.
Okay. So here's the case study that I'm going to share with you. And it's from a community in Southern California. It's built by our partners, KB Home. It's 219 WaterSense labeled homes in Menifee, California. The Southern California. It's a microgrid community. So it has community electric storage. It has heat pump water heaters that are not only efficient, but extremely efficient, very close to the absolute top of the range of what you can get in heat pump water heaters these days. And the average home is about 4 bedrooms, a little under 2,300 square feet on 6,800 square foot lots. It achieves its WaterSense certification by getting a HERS H2O rating system score of a 59. That means that it's 41%, the scale of 0 to 100, more efficient than a code-built home, saving about 61,000 gallons of water a year per home compared to code-built homes. So this is a very efficient, both from a energy and a water use perspective, very efficient community. But in addition to being very, very water efficient, looking just at the energy that's used for water. So again, extraction, treatment, conveyance, heating, everything associated with water. A community of code-built homes in this location. So again, the reference, the code-built homes, which might exist without any intervention, would use about a little over 750,000 kilowatt hours per year. In these, it's adjoining communities, Oakshade and Durango. Whereas because of the water efficiency technology actually put into these specific homes, they're only going to use about 223,000 kilowatt hours per year. So significant reduction that they're able to achieve. If you prefer to look at it in carbon, we're looking at about a little over 400,000 pounds per year of carbon for code-built homes, as opposed to just under 70,000. I'm sorry, this should be pounds per year of carbon for the homes as they're built today. So significant savings, and we'll dig in a little bit to how we calculate that and how we can support it. So like I said, 13.4 million gallons of water saved for the whole community, 219 homes per year. It's about 640,000 kilowatt hours and 358,000 pounds of carbon each year. So how do we get to those numbers, right? They're very granular, they're very specific. They are based on the location of the community, on the water that's going to be used to sustain it, and on the technology that's been put into the homes and how we think the homes are going to use water. And in order to get a real site-specific estimate, we need a few big pieces of data. Number one, we need to know what the mix of water resources. So what water is going to come out of the tap when you turn the handle? Where does it come from? How did it get there? Number two, we're going to need, for each of those sources, how much energy went into taking it there, right? So where did we have to pump it? Where did gravity do the work? Where did gravity do the work for us? How did that impact the treatment that had to happen? And what's the delivery profile and wastewater treatment profile going to be, again, given the site-specific location, given the site-specific location that these homes are built in, because we can't move the homes after they're built. And then finally, we're going to need to know how is water going to be used at the homes themselves. So we need to know is how much water, not just the total water use, but how much of that water is going to be outdoors, how much is going to be hot, how much is going to go down the drain, and create wastewater treatment? These are all the questions we have, and luckily, because this is in Southern California, we actually have a little bit of a better picture than we might elsewhere because of the reporting requirements. So Eastern Municipal Water District is the water supplier in this area. In California, all water suppliers have to make public their water management plans, which include specific mixes of their water sources. The California Public Utilities Commission, the PUC, also releases data on energy intensity per source that is specific to geographic sections of the state. So not only can we say, well, this water came from the Colorado River Aqueduct, but water that comes from the Colorado River Aqueduct and is delivered to this part of the state has this specific energy signature, again, in each of those phases that we discussed. And then because these are WaterSense labeled homes, we get a significant amount of data on what the technology that goes into the homes, and we can model with reasonable confidence how water is going to be used in the homes for those specific based on that specific design and technology. So we've got all our data. Now we've got to put these things together, and we'll start with the water. So these are so if you go into the report and you say, okay, well, where does Eastern Municipal Water District get their water? This is what it looks like, and it's pretty common for Southern California for utilities to have this type of healthy mix of different water sources. But you'll also notice that there's over half of this kind of just says, well, it's water they purchase from MET, which is the Metropolitan Water District. So it's has the role of purchasing and reselling water to a lot of the agencies in Southern California. But that's not terribly helpful, so we'll break that out a little bit further. And again, for purposes here, we're going to assume that there's an even distribution of all of these sources in every drop of water. That's not 100% accurate. If we were to actually go to Eastern Municipal and talk to people on the operations side, they might say it's like, well, yeah, but there's really no intersystem connectivity between where the Colorado River water comes in and where these houses are located. We're not going to go to that level of detail. We're going to sort of assume everything is proportional. But once we include the water from the Met and we break it out, now we've got even more water resources. And again, this would be atypical for a lot of parts of the country, but it's very typical for Southern California. You've got water from all these different sources mixed in together when you turn on water and it comes out of the tap. And again, we can go back and we can get very specific data on all of these values. So each of these sources is going to have its own signature for extraction and conveyance, its own signature for treatment. Some of these things look very similar, and that's just because they're very similar in terms of their water quality and where they're going to get treated. So that's why they tend to have the same values. Likewise, once everything's all mixed together in the system, distribution's pretty flat. We're taking the water to the same place. So 163 kilowatt hours per acre foot of water. An acre foot is it's a horrible unit of measure, but it's what we use to talk about large quantities of water. It's a foot of water stacked on an acre of land. So if you think of like a football field, think of a column of water 1 foot high on that football field. It's about a little over 325,000 gallons. The one you'll notice sort of one holdout in distribution, which is that recycled water, wastewater that we treat and then reuse in homes, actually has a much higher distribution energy associated with it. And that might be kind of a head scratcher, but it actually makes a lot of sense because mostly water that we treat as wastewater and then recycle goes uphill. Naturally, we build water distribution uphill and we build wastewater treatment downhill so that we can use gravity to do a lot of the work. When we bring treated wastewater back up, we're generally going uphill and it has a higher distribution requirement associated with it. So then we can take those numbers and we'll weight them, right? So based on the proportion of the different water sources that are in all of those different sources of water and the energy intensities associated with them, we'll come up with averages. So we'll know that for every on average, every acre foot that's delivered at this community will have spent an average of 1,377 kilowatt hours per acre foot of water on extraction and conveyance. We'll know that on average it will have spent 284 kilowatt hours per acre foot on treatment, so on and so forth. And we'll get very unique signatures for each of these different phases of the water cycle. Then we have to ask ourselves the question of, again, how are these homes going to use water? And for simplicity's sake, we're going to look at this in really 3 different types of water. So something like outdoor water use, as I mentioned before, that's really only supply, right? Once it's sort of emitted, used to irrigate a landscape, it's going to do different things. It's going to infiltrate the ground. It might run off. It's not the end of the story as far as the water goes, but it is the end of the story as far as its energy signature. Water that anything that comes into the house and is going to go down the drain is also going to have the added impact of wastewater treatment. And then finally, anything that we heat obviously is also going to have the heating associated with it. And then if you look at the bottom, I just put national, what we consider to be very conservative national averages for all these numbers, just to illustrate sort of how variable these can be and why I think there really is a benefit, and if you can, getting to a more specific, granular, local estimate, because a lot of these numbers really are quite a bit different than what we would use as a national average. So looking at these communities, again, looking at what we expect the reference, the code built homes to use, looking at water that's used outdoors, cold water that's used indoors, and hot water that's used indoors, as opposed to the code to the actual homes, which are water sense labeled. Obviously, the water use is quite reduced, and we need to know how it's reduced specifically across those 3 categories. And once again, we'll use that number to go ahead and calculate out across all phases. I know I'm throwing a lot of numbers up here. I don't expect you to absorb these actual numbers. I just want you to see sort of the level of detail and granularity. The other thing that can be important about being able to drill down into these specific numbers is that something like heating, well, that's going to happen on site, right? That's on site. It's going to be represented on the customer's, in this case, electricity bill. We know exactly where it's happening, and we can associate the power consumption and the carbon impact with that location. Something like extraction and conveyance, that could be happening hundreds of miles away. And so it's important from a energy and carbon accounting perspective to know not only what the total is, but where that energy expenditure is happening, because it might not be at the same location as where the water is being either used or saved. And then I like to give this as a comparison. So this community, in regards to its water, is really sort of saving carbon in 3 main ways. One, it has the microgrid. So we hope, presumably, we're making this assumption that it's not pulling any energy off the quote unquote dirty grid. It's getting all of its power either from solar panels or drawing from the house batteries or the community battery storage and not having any carbon impact. Number 2, it has the heat pump water heaters, which are obviously reducing the energy consumption significantly. So sorry, the microgrid has no actual energy savings associated with it, but it does have a significant carbon savings. Heat pump water heaters have a carbon savings as well, but they get to their carbon savings by reducing the energy consumption. And finally, we have water efficiency, which is also, which in its case is reducing carbon by reducing the load on energy. Excuse me, not just energy, but also conveyance. So if we were to look at these things in isolation, maybe this is sort of the order that you'd expect to see them in. But I can promise you this: water efficiency is by far the cheapest solution. This microgrid costs millions of dollars. These heat pump water heaters are not cheap. Whereas the water efficiency solutions, efficient as this community is, are really really mostly low cost and no cost solutions that at the same time have tremendous value, not just in the water savings they offer, but also in the energy and carbon impact. So as you saw, a lot of those savings come from hot water. If we sort of turn our attention a little bit and talk about how this might impact other facilities, well, here's just a quick snapshot across different types of CI facilities. And you'll notice that I kind of circled them here, right? Laundry, kitchens, domestic restrooms. These are all places that have substantial hot water use associated with them. And they make up a significant portion of the water used in all of these facilities. So these are really good targets. Like I said, you're going to save energy any place you save water, but you're always going to save the most when you work to reduce hot water consumption. Great way to do that, of course, look for WaterSense labeled plumbing products, shower heads, and lavatory faucets specifically. You will always save energy when you use these other plumbing products and these other and the irrigation technologies. But anything that's going to have hot water in its savings are really going to give you the best bang, absolute best bang for your buck. Again, I'm not going to dig super deep into this, but we have other webinars that deal exclusively with restrooms, as well as exclusively with auditing facilities. So just to give you an idea of some of the things that you look for if you have an existing facility and you want to either just for the water savings, just for the energy savings, or as we would encourage, looking at both of those things together. Look at the restroom fixtures. Look at things like fixture count, fixture type, whether or not they're mounted properly, and whether or not there's any sort of reason to believe they're worn out or scaled up or no longer performing the way that they should. Again, just some of the examples of advice we have for auditing, measuring, and making improvements on restroom fixtures. And a quick snapshot of some of the potential savings. So newer facilities, again, was still probably going to be able to go into a relatively new facility and find plenty of water savings. But for those of you with older facilities, well, there's a pretty good chance you might find some of these 3.5 gallon per flush toilets available. Whereas now we've got really high performing, high efficient, cost-effective toilets that are WaterSense labeled, available for 1.28 gallons per flush or less. So there's really significant savings available, again, for all buildings, but certainly for older pre-1994 buildings. Laundry is another one of those places. Significant water savings here, but also significant energy savings, in part because a lot of the water used in laundry facilities is heated. So it's got that sort of double penalty for energy consumption. We don't label clothes washers in WaterSense, but our friends at Energy Star do. And because of that connection, water consumption is a big piece of the certification and something you can look for when you're ready to replace equipment. Commercial kitchens, another place where there's significant hot water use and significant opportunity to really dig in and make sure that you are using water as efficiently as possible, while also saving a significant amount of energy. I believe this is another place where we have an entire webinar with case studies singularly focused on commercial kitchens. So those of you with facilities that do have commercial kitchens, a great place to look into for water and energy savings. And that brings us to cooling towers. So it's been pretty straightforward up to now in the conversation, right? Like I said, anytime you save water, pretty much any water you use in a home, any water you use in a restroom, any water that you save is going to save energy as well. Cooling towers are a little bit trickier. Cooling towers use water to save energy. That's fundamentally what they do. And they can do that because water has this sort of great property of being able to absorb heat, move it someplace else in the building, and then dissipate it. It's a super useful thing to be able to do in the built environment, and helps us move water around. That's fine. You know, we're not anti-cooling water in WaterSense, though it's worth noting there are some jurisdictions, some places in the country where they're really starting to crack down on this and starting to move away from it, where they're saying, no, we need the water too badly, and we're going to make you use air-cooled equipment that, yes, might not be quite as efficient from an energy perspective, but it's because we need the water. So we are starting to see that. The other thing we always encourage people to do is, you know, ask the question of whether or not water cooled chillers are really the right solution. I think for a lot of years there was this sort of default to assume that yes, just at a certain size of building, it automatically was, but I don't know that that's always the case. And if we put numbers to it, cooling towers compared to air-cooled equipment tend to save somewhere between 0.3 and 0.6 kilowatt hours per ton hour of cooling. Right, so somewhere in that range, which adds up a lot. If you have a big facility and you have a lot of cooling load, you have a lot of ton hours. 0.3, 0.6 kilowatt hours per ton hour of cooling can be quite significant. At current average national commercial electric rates, that's about 4 to 8 cents per ton hour of cost savings. The flip side of that is that in order to get that energy and the cost savings associated with it, we are going to use water, and that's going to be somewhere between 1.5 to 5.5 gallons per ton hour of cooling. So every say half gallon or half kilowatt hour per ton hour of cooling that we save is going to use somewhere in that range of gallons in consumption, and that at current national rates is about 2 to 6 cents. So you'll notice if your point is to save operating costs with a cooling tower, these numbers overlap. So if you have an inefficient cooling tower and you think you're saving money by it because you're reducing your energy bill, well, you might not be, because if you're using more water, which is, again, still cheap, but not as cheap as it used to be, then you might not be coming out sort of in the black, as they say. So, water-based cooling isn't always the best solution. It's important to ask that question. Well-run cooling towers definitely have the propensity to stay sort of on the right side of that equation, so to speak. But just by way of example, I threw up Seattle here, which is someplace that's actually known in the grand scheme of things for having relatively low electricity costs and relatively high water costs. And you see, compared to the national numbers, I said how much these really sort of overlap. So again, I think that the thing to take home there is really just that if you're not operating your cooling tower efficiently in regard to energy or water, you're not going to be saving money. You're going to be using more and wasting water at the same time, which is not something that we really want to do. The other thing, maybe I should have put this first, that we always emphasize: single pass cooling is not something we encourage. Again, this is the reason we use cooling towers is so that we can use water-based cooling and still use that water more efficiently. If we're using single pass, then you're really just using that water once and then running it down the drain. So a cooling tower can be about 40 times more efficient than single pass cooling because of its ability to circulate that water around and reuse it multiple times. Our goal with cooling tower efficiency, just using my sort of simple schematic here, is to increase the number of times that we can, you can see my pointer, maybe not. Anyway, it's to increase the number of times that water can move from the cooling tower, move from the chiller, pick up heat, move back to the cooling tower, and dissipate its heat before we are going to lose it to drift losses, before we have to use blowdown to take some of that water out because of its concentration. concentration and put more water in to make up the supply. So these are the things: eliminating drift loss, um, minimizing the amount of blowdown we have to do, controlling for conductivity, and thereby limiting the amount of makeup water. Those are the things we target in cooling tower efficiency. A lot of times people will ask, well, how do I limit the evaporative losses? And the answer is you don't want to limit the evaporative losses in a cooling tower because that's what's creating the cooling. If you're going to limit the evaporative losses, you may as well not have a cooling tower and just move to something else because that's what's providing the cooling. This is something that we have lots of data, lots of information on in WaterSense. I believe our last webinar in this series was on mechanical systems and touched heavily on cooling towers. We have an entire best management practice guide in WaterSense, which you can easily find online, that will help you really give you advice on how to increase these cycles of concentration. Again, that's our goal with efficiency in cooling towers. We want to move that same water around as many times as possible before we have to send it down the drain or before we lose it to drift losses or something like that, so that we can continue to use it to cool the property, but be as efficient with the water as we can. Again, just sort of some clips from our BMPs, as well as the previous webinars we've done, that will take you through things like controlling for conductivity, making sure that you're only blowing down water when you really have to, and using treatment to minimize that as much as possible, so you can get as many cycles of concentration and use the water as efficiently as possible in the process. As I said, this is definitely more of a more conceptual webinar than we normally do. But here are some of the places you can find tools. So if I've piqued your interest at all, if I've sort of convinced you that yeah, I can go out and I can save water, and that's going to be good for my energy savings as well. Here are some of the places that you can find all the tools that we have available. I mentioned our best management practices a couple of times. We have chapters on all of these things that I mentioned, on sanitary fixtures and restrooms, on kitchen equipment, on outdoor water use, on mechanical systems. All the things that have come up as potential areas where we could target and save water and also save energy in the process are really addressed in detail in the best management, in the BMP guides. And then in the near future, we'll actually have a new one, which is specifically on the water energy nexus. Again, this is much like this webinar. This is going to be perhaps a little bit less focused on practices, but more focused on helping you understand what the connection is and how you might be able to utilize that at a specific property and incorporate it into your management techniques. And then we also have, in addition to the BMPs, some facility-specific tools that can help you really tackle these individual projects when you're on site and need to evaluate a facility and understand where the best improvements lie. And I believe everyone's going to get a copy of this, so that's why we put sort of so many different resources in it, because you all get links for any of this information that you find useful. And then once again, all of the webinars we've had in the past, if you weren't able to join us for them, they are available. You can go back and find the recorded versions and really dig into the specifics of any one topic that we've covered today, in addition to the final webinar for the year coming up next month. And I think I was pretty good at staying to my 45-minute time limit, so that we left plenty of time for questions. Did I do okay, Tara?
Yes, you did great. Thank you so much, Jonah. That was a really helpful presentation. I even learned a little bit myself. So always good to learn something. So thank you. We have a couple of questions that have come in and a few that we had from when people registered for the webinar. So someone said, I think this may be a comment. It seems curious that on-site roof rainwater collection, treatment, and offset of potable water needs inside the home is unmentioned. Its electrical and carbon footprint are the lowest of any source.